Section 3.1 on terminology. This is example number 2 in this section. What we're going to do is look at this situation with rolling of 2 dice. One of the things I want to point out is, as we're looking at the table, is that a lot of situations, and the reason why I have the table is that to point out that there's 36 different outcomes of a rolling of 2 dice, and realize that when 2 dice are rolled, this is one of the different outcomes that could appear as you're looking at the table, and I have it colored as if you had one red die and one blue die, so that you could visually see that there's 36 outcomes. And one thing to consider is that if we rolled one die at a time, then each die itself has 6 sides, and then I want you to see that it's a multiplying effect. So if we rolled the red die first, it has 6 possibilities out of it, and then if we rolled the blue die, it also has 6 possibilities. Well, if we go to multiply 6 times 6 together, and that gives you the 36. So it is a multiplying effect in that way. You can see by the grid that we have all 36 different outcomes stacked up all together. And so what we want to do in this situation with this one, part A, part B, C, D, and E, there, including F, is to look at adding the 2 numbers together. So, let's say the red die was thrown and the blue die was thrown, or even both at the same time. With the numbers that come up, doesn't matter the order in that way, you just add the numbers together, the total number of, dots, like on the die that are visible, and that's what we're looking at here in this first example. So for part A, it says that sum the S is equally likely. And one of the things I want to point out too is that you see the number 2, where they're alluding to that for the number 2, like 1 plus 1. Well, that's 2. And that's where the idea of 2 comes in. So coming down over here, what's the probability of getting 2? Well, we have to consider that how many of those are possible. Well, there's only one outcome that's a 2. And if you look at the rest of those, you'll never have an outcome that's, the same as that. So for example, if I keep going here, like the next one, 1 plus 2 versus 2 plus 1, those give us our 3. So kind of label it as like our 3 diagonal there. Next one, 1 plus 3, 2 plus 2, and 3 plus 1 is 4. So you notice like all these different outcomes, they kind of appear in a diagonal. Like this one with the 1, 4, 2, 3, 3, 2, and 4, 1, that's like our 5 diagonal in that way. Well, we know there's only 1, 2, and it comes down here, if you keep going through all of these, like this one's our 6. And then the greatest number we could get here is 7, with all the different outcomes that add up to a 7. Then coming down underneath that, we have 8, but of course it's less probable. And then down to the last one, down at the very bottom here, 6 plus 6 is 12. So we got everything, of that in between. Like this next one would be, the number 9. And then a couple more here. We have, the 4, 6, 5, 5, and the 6, 4. Of course, that's 10. And then, probably last one here, and then we get 11. So then in this way, when I look at the number 2 here, I want to know how many of those added up to a 2, versus here for a 3, there were 2 outcomes that add up to a 3. There are 3 outcomes that add up to a 4. So when I want to fill out the table down here, that's what I'm accounting for. There's only one outcome that is a 2, that where the sum of the 2 is a 2. That's 1 out of 36 would be that probability. Going to the next one, how about a 3? Well, there were 2 outcomes up there. That would give you 2 out of 36. And if you want to simplify that, of course, that would be 1 out of 18. Next one, how about a 4? And you kind of notice that if I just look at the frequency without figuring out the probability, like 4 would be a 3, 5 would be a 4, 6 would be a 5, and 7 would be a 6. 7 is the most likely. Well, those are out of 36. By turning that frequency into a probability, you divide by the total number of outcomes possible. And then after the 6, it starts to scale down. It goes, because you'll notice up here for the 8, well, let's go ahead and count them here. Let's go back over to this list here that we notice that there are, there's 1, 2, 3, 4, 5 outcomes. That's an 8. It starts to scale down. So then this becomes 5 out of 36, and then we got the 9's 4 out of 36, 3 out of 36, 2 out of 36, and then last one, there's only 1 12, where that's the 2 6's, and that's 1 out of 36. If we went ahead and simplify these, we could. Like here for the 3 out of 36, that would be the same as 1 12th, dividing those by 3. 4 out of 36 is the same as 1 9th. 5 out of 36 doesn't simplify, but 6 out of 36 does. So that would be the same as 1 6th. And then 5 out of 36 doesn't, of course, and then we got 4 out of 36, which simplifies to 1 9th. 3 out of 36 is back to 1 12th. Then we have the 1 out of 18, 1 18th there. And that'll complete some of the simplify. There are going to be probably some questions that ask you to simplify these, and then maybe others that will ask you to turn it into a decimal format. But we're going to use this filled out table here, and this is called a probability distribution function. This is going to be important later. So I'm going to highlight this, and we're going to call this it's called a PDF. Probability distribution function. Unlike the I think it's called the other form of PDF, portable, dense, I think it's called, I don't remember the D is, PDF format. What if I ask a student to send me something in PDF format, which is kind of redundant because F stands for format. But here we get completely something different. Probability had it first before PDF came along, and it stands for probability distribution function, or it could stand for probability density function. That's as compared to its other little buddy called the CDF, or the cumulative distribution function. So both are important. Of course, we won't talk about cumulative distribution functions. It's a little too early for this class to do that, but PDFs is what we're going to try to figure out, and that'll lead into chapter 4. So I figured to introduce the property right now. We'll actually pick up the same problem later. But now let's use the following table to figure out the following here. Find the probability that the sum is a 4. Well, in the list here, if you actually we kind of bring this answer down here, that we have the 4 is right there. We've already done the table, and then next one obviously there is the 6. What's the probability giving me the 6? Now that we already have the table filled out here, but just to iterate on the concept where the sum is a 4, you can see here that we've got 1, 2, 3 outcomes where the sum is a 4, and that's where we get that 3 out of 36. And of course that equals to the same thing as 1 12th. Next one is 6, and we know we have a count there. If you want to look at the table, we have 5 of those outcomes. That's where the sum is a 6. That's out of 36, and of course there's no equivalent to that because 5 is not divisible by any of those other factors. Next one here about the evens. I want to count there at the top how many of those are evens, but if we want to highlight them here, we could do that as well. Where the sum is an even, well, 2's even, 4's even, 6 is even, 8's even, 10, and 12. So what I want to do is add up all those probabilities together. In this list here, I want to take 1 out of 36, plus 3 out of 36, plus 5 out of 36, plus the other 5 out of 36. So basically it's 1 plus 3 plus 5 plus 5 plus 3 plus 1 out of 36. So again here we've got 1 out of 36. I'll make that a little bit smaller. Plus, next one would be for 4, that's 3 out of 36. Plus the next one for a 6, that's 5 out of 36. And then we'll have a repeat there of the next one. 5 out of 36, and then we keep going. Next one for the 8 is another 5 out of 36. Then we have a 10, kind of scales back there. 3 out of 36, plus the last one, the 12, would be only 1 out of 36. And if you end up adding those all together, then we get a total, we should have 18 here. 1 plus 3 is 4, 4 plus 5 is 9, 9 plus 4 is 14, 14 plus 3 is 17, 17 plus 1 gives us 18. So 18 of those where the sum is an even. If you kind of follow them here, what I'm looking at is on this grid, which ones are even. Again, the sum is 2, 4, 6, 8, 10, and 12, but not considering those, but actually counting those, and you would come up with 18 of them. In other words, since the total is 36, half of these are going to be even, which obviously would make sense. We're a 6 by 6 grid. So you can simplify this and say that 1/2, or you could also say that you have a 50% probability of picking, or actually when you roll the two dice, that the two numbers added together is going to be an even. For part E there, the number of dots is strictly greater than 9. Let's go ahead and look at that. Let me dissect the table here again. Strictly greater than 9 would be 10 or more. So if I just kind of erase everything here that we don't need, I'm just looking at this case here, the 10 or more, and then you physically want to count those. That you've got 1, 2, 3, 4, 5, 6. So that probability being more than 9 is 6 out of 36. Which of course is equal to 1/6. The last one here says, suppose that we roll the dice 7,200 times. How many would you expect to roll a 7? Well, that goes along with the concept here, and we'll talk about this later, that the number of times rolled, and you want to multiply that times, I'll just do that, the probability of getting a sum is a 7. Well, we know for this instance here, we'll assume that the number of times rolled is 7,200. And then the probability of getting the sum is a 7. Let's go back up to our table to determine that. And it would be right here that we've already figured out for the sum is a 7 is 6 out of 36, or 1/6. So all that we need to do is multiply the number of times rolled times that probability. That will give us the total of the 7,200 times that we could mathematically expect. There I'm talking about a little mathematical expectation there. That would come up with a sum of 7. So just imagine this. If we had a computer that randomly generated, 7,200 possible rolls, this is our probability of getting where the sum is a 7. Let's go ahead and figure out how many that would be. So we have the 7,200 times 1 divided by 6. And there we get 1,200. So we could expect here 1,200 where the sum is a 7. And I'll put there 7s. And I'll also include the concept of except. I'm sorry, expect. Not exec. It's kind of different. Expect and aspect. It's getting pretty late. We could expect 1,200. And so when we get into 4.1 and also 4.2, talking about mathematical expectation, it'll be strictly that kind of using that concept of multiplication to get that across. That's the same thing, by the way, as the average of tying that in with mathematical expectation. All right, so this is example number 2 in this section. Kind of a slightly different concept, but more or less here working with this thing, this grid here, and I'll just label this. This thing here is more or less our sample space. So that gives us our idea already given the 36 possible for our sample space and using our sample space to find probabilities. That was the main thing for this exercise, is to do that. Maybe it's unfortunately I already gave you the sample space, but to utilize and see the importance about actually visualizing the sample space is very important to be able to find probabilities. So actually get into more activities, I want you to develop your own sample space. You can use a tree diagram or a table to do that, and once that's developed, it makes finding probabilities a lot easier to do. All right, this will wrap it up here for section 3.1, example number 2 on terminology.